Hello everyone, my name is Jay Sharma, and today I will be introducing you to mathematical proofs. So I want to start by sort of talking about the an introduction to mathematical proofs, where you would see them, as well as the significance behind why we do mathematical proofs. So the first time you would see a mathematical proof would be in the context of a math textbook. This is where textbooks try to convey a point beyond the shadow of a doubt. They try to communicate their results and make you understand why a certain thing is the way that it is. And so they use logical arguments to develop a sort of conclusion that they can use as a postulate to sort of encounter new examples and try to solve other problems as well. However, every other time that we do a mathematical proof, for example, the Pythagorean theorem, we have numerous proofs, both algebraic, geometric, and then that raises the question, why do we need so many proofs? Well, this conveys some aesthetic value, and it shows true understanding of the concepts, and it relates these different types of math together. As I said, there are both algebraic and geometric and picture proofs for the Pythagorean theorem. So by doing all of these different types of proofs, we sort of entwine all of these subjects and show them that these subjects that are look so different, they're actually just a part of the same exact topic. So before we get into and get our hands dirty with proofs, I want to express one big thing, which is that proofs are supposed to be about writing. So you're supposed to write, write, and write. So proofs are a journey. They're like a story for you and the reader. So you're taking your reader on a journey through this proof using some logical concepts and trying to show them your point. So you would use first person because you are doing the proof with the reader, and you would say, we will now show that blah blah blah. So you have to say we, so include yourself as well as the reader. As In addition to that, so like any other story, um, proofs have words. So um, words meaning full words like complete words, and as well as capital letters at the beginning of every sentence, punctuation at the end of every sentence, as well as your other grammar mechanics. So you should use your words to convince your reader to believe in the proof. So after your reader has read the proof, they should be able to say, yes, I believe that this topic that the writer is writing about is in fact true. Now we get to the different parts of a proof. So there are several different parts to a proof that are pretty important, and you'll see this if you read different proofs, they'll mention these names. So I would like to clarify those. So conjectures are the question or the whatever we wish to prove. So there are many different types of conjectures, such as the Goldbach conjecture down here. So you can search that up on your own. And there are many, many conjectures that have not yet been proven. Goldbach conjecture is one of them, and it's a very famous conjecture, so you can try that out on your own. So in addition to this, there are the theorems. So these are like proven statements or postulates that we can use to prove other proofs. And a smaller version of a theorem is like a proposition. Other definitions of parts of a proof are, of course, first definitions. This is where you don't really have any argument to say. You're just sort of defining. Maybe you're defining some variables. Maybe you're just defining your problem. Or this is a part of your proof where there is actually no argument, and you're just stating something for the reader. Lemmas are an intermediate step in proofs. So before you prove the actual theorem that you're trying to prove, you would first prove a lemma. Sometimes you would prove a lemma. So that this is an intermediate step which you can then use to prove your original problem. And similar to this is corollaries. So as soon as you prove a certain theorem, Corollaries are just theorems that when you prove them, there is a result that quickly follows right after that. So I want to start by discussing one type of proof. So this is called proof by contradiction. Proof by contradiction is a very simple idea, yet is a very powerful idea that's used in math. The basic idea is to first assume whatever statement you're trying to prove, first assume that that statement is false, okay? And then prove that you arrive at an impossible conclusion. So, in doing so, basically, you show that the statement cannot be not true. It cannot be false, therefore, it must be true. Okay, this may seem a bit abstract, so I'm going to introduce an example. But first, I want to introduce some definitions to you so that we can work through this example together. First is a definition of a rational number. So a rational number is written as a fraction. You can write a rational number as a fraction or a ratio between two different integers, or they can be the same integer, but they're two integers that are written in a ratio. Okay, so numbers that cannot be represented this way are called irrational, and of course numbers that can be represented this way are rational. Then you have the greatest common divisor, or the GCD. It's commonly called the GCD, denoted this way. And it is defined as the largest number that divides both x and y. Okay, so for example, if I wanted to take the GCD of 2 and 4, I would try to find what is the largest number that divides not only 2, but it also divides 4. Well, 2 is the largest number that divides both of those numbers, right? So you end up like finding the GCD to be 2. Okay, and a rational number, our last definition, a rational number is said to be in lowest terms. So you might have heard this in one of your math classes. So a rational number is said to be in lowest terms if the GCD of x and y, okay, so like our rational number is x divided by y, so the GCD of x and y is 1. Okay, so that means that x and y do not have any common factors greater than 1. So the GCD of x and y equals 1, that statement right there means that the largest number that divides not only x, but also y, is 1. No greater number divides both of them. Okay, so they're in lowest terms when it's written that way. And they're also said to be relatively prime to each other, co-prime. And then one remark for you is that if a rational number is not in lowest terms, we can actually bring them in lowest terms by dividing both the numerator, x, and the denominator, y, by the GCD of x comma y. And then basically what will happen is since you divide by the GCD in the top and bottom, you essentially get that the GCD becomes 1. Okay, and so in an example, right, that you were talking about the GCD of 2 and 4. So if we consider the fraction 2 over 4, that is not in lowest terms because the GCD is not equal to 1, as said in our definition over here. Our GCD needs to be equal to 1. So what we do is we divide both the numerator, which is 2, and the denominator, which is 4, by the GCD of 2 and 4, which we found earlier was 2. So if you can imagine with me, 2 in the numerator, 4 in the denominator, we divide both the numerator and denominator by the GCD, which is 2, and we get 2 divided by 2 divided by 2 is equal to 1. 4 divided by 2 is equal to 2, and if you can imagine with me, that becomes 1 over 2, okay? Okay, so hopefully you know a little bit now about rational numbers and GCD and lowest terms. So using all of this, I want to go back to the idea of contradiction, proof by contradiction, and introduce you an example to make more sense of what this is all about. So I want to prove now that the square root of 2 is irrational, okay? So the square root of 2 is the number which when you multiply by itself, the positive number, which when you multiply by itself gives you 2, right? So we will now prove that the square root of 2 is irrational. Now, first you prove that the square root of 2 is irrational by assuming that it is rational. So we're doing proof by contradiction, right? So we assume that the opposite of our statement is true, okay? So we assume that the square root of 2 is a rational number. It's a rational number, okay? And therefore, it can be written in the form a divided by b in lowest terms, okay? And this is going to be a really important thing for our proof. It's in lowest terms, which means that the GCD of a and b is 1, okay? So we assume that it is rational, and then we're going to try to play around with the problem and find that we yield an impossible conclusion, and then therefore, by contradiction, the square root of 2 must not be rational, it must be irrational. So let's try to find out how we can do that. So remember we said that we're going to assume that the square root of 2 is a rational number so that it can be written in lowest terms a divided by b. So this is what we get. Now we square both sides. We square both sides, we get rid of this square root of 2 and it becomes 2, just 2. And we square 8 over b, we get a squared over b squared, okay? And we can multiply both sides of this by b squared in order to get a squared equals 2b squared, okay? So this is just a rearrangement of this equation, okay? So over here, right, from this right here, we can deduce that a is even. Why is that? Again, you could prove this by proof by contradiction, but it's much easier to just say that if this side is, for example, if this side is odd, right, then the square of an odd number is always going to be odd. And you can use a little bit of modular arithmetic to try to prove this, that the square of an odd number is always going to be odd. However, this right side over here, this is an even number because b squared is an integer, and any integer multiplied by 2 is an even number. So a squared must be even. However, if a is odd, then a squared, turns out that a squared is also odd. So if this side is odd, this side is even, it doesn't match. That's impossible. So a actually has to be even. So when we square an even number, we actually get another even number. And this is right here. Sorry. This is right here. The square of an even number is equal to an even number, okay? And so just try to understand from this, what I'm trying to make you understand is that a must be even because the right side over here is even. Okay, that's all I want you to take away from this. Now we can actually write, since a is an even number, right? We can write every even number as 2 times something, right? So we can write a as 2 times c, okay, for some c. Then our equation from before, right? This guy right here, this equation right here, if we replace a is equal to 2c, because 2c means an even number, right? And a is an even number as we just showed. So a equals 2c, we're just substituting that into this equation right here. Okay, hopefully that makes sense. Then our equation, this guy right here, becomes, we just substituted the value for a, we just substituted 2c, okay? And now we're going to expand both sides of this equation. Well, this side right here is already expanded, but this side right here, I can actually make that into 4c squared, okay? 4c squared is equal to 2b squared, and we can divide by 2 on both sides of this. And we end up getting 2c squared is equal to b squared, okay? Just dividing by 2 on both sides of this. Okay, so now, by the same logic as before, b squared is equal to, so the b squared is equal to 2 times some number c squared, right? Remember that right here we did the same thing for a. Right over here, remember, just recall over here we proved that a was even because this right side over here is even, so therefore a must be even. Similarly, we can prove that b must be even because right here, this this is even, so the right side must be even, and in order for that to happen, b must be even. Okay, so we have that a is even and b is even. Okay, because of these two equations right here, these two equations. Now we think about this for a minute. So over here, let's think about the definition of a and b. A and b are supposed to be the rational form of this. But remember, it's in lowest terms. It's in lowest terms, which means that the GCD of a and b, by definition of lowest terms, must be equal to 1. Okay? Therefore, the largest integer to divide both a and b is 1. Okay? So by our definition or assumption up here, okay? However, they're both divisible by 2, which is larger than 1, right? So the GCD, the greatest common divisor, the greatest number that divides both a and b, must be at least 2. And therefore, a divided by b is not in lowest form, okay? And that contradicts our assumption that the square root of 2 can be rational. And therefore, if it's not rational, the square root of 2 must be irrational. And therefore, the square root of 2 is irrational. Okay, so I want to go over this again. So we proved that the square root of 2 is irrational by first assuming that it was rational. Okay, so we assumed the opposite of our statement. Then we played around with our problem, and then we found that our initial assumption that it could be written in the form of a rational number, that assumption was false. Therefore, we showed that the square root of 2 must be irrational. It cannot be rational because that contradicts our assumption, right? Therefore, it is irrational. Okay. And that's how you would do proof by contradiction. Now, I just want to talk about this white square, okay? So at the bottom of our proof right here, you see this white square. What does this really mean? I mean, in proofs, generally, you would put something like this at the bottom. So this stands for quod erat demonstrandum, or that which has been demonstrated, okay? So this symbolizes that our proof is actually done. And we can sometimes abbreviate quod erat demonstrandum as just Q and then E and D. So QED is sometimes in place of this white square over here. And sometimes you also have a black square as well. So those are ways that we can show that our proof is done. Okay, so we're just going to summarize our strategy of proof by contradiction. So to show that a statement is true, we sometimes start by assuming that the given statement is actually false. Okay, then we go around and we play with the problem. Okay, we play around with the problem, and then we find that this cannot be the case because we arrive at an impossible conclusion. Okay, so remember, we assumed that the given statement was false. Then this false right here, the statement is false, we proved that to be impossible. So the statement that this statement is false is impossible. Therefore, the statement must be true. So we have this kind of double negative thing going on. Okay, and in summary, this is called proof by contradiction. Okay, so I recommend you to pause the video right here and try to use our rational numbers as and lowest form, GCD, all of those tools that we just developed to try to attempt these two problems right here. Okay, hopefully you've given a go at this at these two questions right here. Now we're going to move on to induction. The essential idea behind induction is first we prove this a certain statement, right? So we are trying to prove the statement, a certain mathematical statement that is, for some numbers, okay, very generally. So we start by proving it for n equals a, okay? So like if we wish to prove the statement for some n, we start by proving it for some n equals a, and this is called the base case, okay? Then we say that, okay, suppose for a minute that it holds for some arbitrary, like our statement holds, our statement for n holds for some arbitrary value of k, okay? Then we play around with the problem once again, and we prove that n equals k plus 1, so k plus 1 also satisfies the statement, okay? And then therefore we can say that, remember, we proved that n equals a holds, right? N equals a, or the statement, in other words, like the statement holds for a, right? And we proved that if it holds for some arbitrary value of k, then it must hold for some k plus 1, okay? So we proved it for a, and therefore, letting a equal k, right? Therefore, the statement also holds for a plus 1. And then we can also use a plus 1 to prove that a plus 2 satisfies the statement, because if we substitute a plus 1 for k, a plus 1 is equal to a plus 2, and we end up finding that a plus 2 satisfies the statement. And then we can keep on going like this. We can keep on going. So we can do a plus 1, a plus 2, a plus 3, and so on. We can find that every number greater than a um, holds for, like, this statement holds for all of those numbers, okay? And so induction is typically used when we wish to prove the statement for all integers, okay? So if we let a equal 1, right? So by all integers, I mean all positive integers. So if we let a is equal to 1, then we get our base case is 1. Then from there we can remember that a implies that a plus 1 will work, and a plus 1 implies that a plus 2 will work, and a plus 2 implies a plus 3 will work, right? And so remember, a we are substituting as 1. So we have proved in our base case that 1 works. Then by this, right, 1 plus 1 works, which is 2, right? So 2 works. So 1 works and 2 works. So similarly, a plus 2, 1 plus 2 equals 3. So 1, 2, and 3 work, okay? And then 4 will also work. And then 5, that 5 implies 6. 6 will imply 7. 7 will imply that 8 works. 8 will imply that 9 works, right? And so just think about this for a second, and it might be helpful to visualize this in the form of a domino effect, which we will be talking about in a second, okay? So, but like, so more formally, in order to show that a statement is true for all positive integers, or in order to use induction, that is, more generally, we can use induction to show first that the statement is true for some base case, some arbitrary base case. And usually we choose our base case to be maybe 0 or 1 if we're proving for all positive or non-negative integers. And then we show that if it is true for n equals k, we prove that it is equal to, it works for n equals k plus 1, okay? So 0, so if our base case was 0, right? 0 would imply 0 plus 1, which is 1, and then 1 would imply 1 plus 1, which is 2, 2 would imply 2 plus 1, which is 3. And so we get this pattern of 0, 1, 2, 3, and so on. And so you can visualize this as a domino effect. So if we prove the base case and then we prove that um, like you can actually extend this to some value plus 1 so that n equals k to n equals k plus 1 thing. That's essentially like knocking the first domino. You're knocking over the base case, right? The base case knocks over the next number, and you prove it for the next number, then you prove it for the next number, and your domino effect keeps on going on, and we knock over all of the dominoes in the sequence, thereby um, so remember that these dominoes all represent numbers. So we're sort of proving this for individual numbers. Okay, so it continues on infinitely. We keep on proving it for more and more and more and more and more integers. So try to think about this and understand it. It's like a domino effect. Okay, and then we will be looking at this sum. So 1 plus 2 plus 3 all the way to n. So sometimes you may have wanted to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way to some number n, and it may have been quite tricky, but now we're going to prove that this value right here is just an elongated form of this shortened version right here, n times n plus 1 divided by 2. Okay, so we're going to prove that these two values are equal using induction. Okay, and you might be wondering, so like this right here, this is a strange formula. So where in the world did you get this from? Well, we're talking about mathematical proofs, so we're not necessarily going to derive everything here. And so that's called derivation, right? Meaning like, where did we get this formula from? Well, if you were creating this formula for the first time, then you would come up with it by finding some way to get at this formula, and that is called derivation. Okay, but we are talking about proofs, so that doesn't really apply here. So we're given this formula, and we're just asked to find that these two statements are equal. Okay, so we're given the formula n times n plus 1, and we're trying to prove this for all positive integers. So we start with 1, okay? Then we want to prove that it works for 2, then 3, then 4, and so on. But we have to start with a base case. Remember the domino principle or induction, right? We have to knock over that first domino by proving the statement for the base case. And the base case in this example is the lowest number for which we want to prove it. In other words, 1. So we can prove it for 1 very easily. So 1 is the smallest positive integer, right? So we use that as our base case, and then we plug in our formula. So remember, we are trying to prove that 1 plus 2 plus 3 plus 4 all the way to n is equal to this formula right here. So let's try to compute this guy when n is equal to 1. Well, when n is equal to 1, then it's just 1, right? There's nothing added to it. So on this side of the spectrum, you just get 1, okay? And then if you think about it, if we replace this n value with 1, we have 1 times 1 plus 1, right, divided by 2. And if you compute that, that becomes 1 times 1 plus 1 is just 2. So 1 times 2 divided by 2. 1 times 2 divided by 2 is just 1, right? So we got 1 over here as well. So we got 1 up here, which was very, very obvious. And we got 1 down here with some basic just calculation, right? So we end up getting that the statement actually works for 1. Both sides of this are equal to each other. Okay. Now we're going to do our 2 induction steps. So we're going to start with the inductive hypothesis. First, we will assume that the formula n times n plus 1 divided by 2 calculates the sum for the first k positive integers. So in other words, we assume that this statement holds true when n is equal to k. Now our job is to do the inductive step, or show that the statement also holds true for n equals k plus 1, because we assumed that it was true for k, for some arbitrary value of k we haven't defined yet. Now we're trying to prove that it is also it also holds for n equals k plus 1. Okay. So what we would do is we would try to evaluate both sides of this original conjecture right here. Okay, so we are going to just write both of these guys independently from each other. Okay, so first we're trying to calculate 1 plus 2 plus 3 plus 4 all the way to k plus 1. So we write that down, 1 plus 2 plus 3 all the way to k plus 1, right? That's our definition, right? And that was given in the statement of the conjecture, right? That's what we're trying to prove. So now we use our inductive hypothesis here. We recognize that this part right here, if you can see what I'm outlining with my mouse, everything from 1 plus 2 plus 3 plus 4 all the way to k. Remember that we can actually represent this by the inductive hypothesis. Remember, we assumed that it works for k. So we assumed that this value right here can actually hold for k times k plus 1 divided by 2. Okay, so we can actually replace this value right here for the first k values over here. And that's a neat little trick, right? So we take this part of it and we just replace it with our formula that we assumed to have worked. Okay, so now remember, we have our original sum, which is 1 plus 2 plus 3 all the way to k, plus k plus 1, right? And we substitute this value right here, okay, that I'm outlining with my mouse, with k times k plus 1 divided by 2, because we know that that works due to our inductive hypothesis. Remember, which is just an assumption for now, okay? So now there's a k plus 1 over here, and there's a k plus 1 over here. So we think about factoring. So we factor out the k plus 1. So if you factor out the k plus 1, you'll see that k plus 1 can be factored out to get k divided by 2 on this side, and then k plus 1 can be factored out to get just 1 over here. Okay, so we end up getting k plus 1 multiplied by k divided by 2, remember? K divided by 2, and then plus this, just, if you factor out k plus 1, you just get 1. So k divided by 2 plus 1 multiplied by k plus 1. So k plus 1 multiplied by k divided by 2 plus 1. Okay, so look at that closer if you don't quite understand that yet. Okay, so we can actually sort of write this as a common denominator, right? We just fuse the denominators by multiplying 1 by 2 over 2. And then we essentially just get that k plus 2 over 2 is the same thing as this expression right here. Okay, so we just substitute that value in. We substitute that value in, and then we end up getting that k plus 1 multiplied by k plus 2 divided by 2, right? Which is just sort of substitution from our value before. Now we get that this is equal to, when we put this guy in the numerator, we get k plus 1 multiplied by k plus 2 divided by 2. And remember, we have to sort of check that the other side of our conjecture satisfies or is in the same form as this as well. So let's try to compute that formula for k plus 1. And you'll see, if you sort of rewind, check it a little bit, you'll see that if we replace k plus 1, sorry, we replace n with k plus 1, we get, from our formula that was given to us in the conjecture, we get k plus 1 multiplied by k plus 1 plus 1 divided by 2. and that equals k plus 1 multiplied by k plus 2 divided by 2. So the formula, the random formula that we were given in the conjecture statement, when we evaluated that for k plus 1, we got the same thing as if we had just done the thing from scratch. Okay? And so we realized that these two guys right here are actually just the same. And therefore, we have proved that if the statement holds for k, then it holds for k plus 1. Then remember, we proved it for a base case, right, which was n equals 1. Then remember, 1 implies 1 plus 1, right? It implies 1 plus 1, which is 2. So n equals 1 implies n equals 2. Similarly, if we plug in k equals 2, then we essentially get that because it works for n equals 2, it works for n equals 2 plus 1. And so we repeatedly just use this conclusion that we came up with. And so therefore, by this domino effect that we have proven the formula works for all positive integers n. Okay, so I want you to essentially pause the video and try these two problems out on your own. And these are very, very similar to what we just did. So use induction to prove both of these. Okay, hopefully you've given that a go, and hopefully you've proven it. If you don't know how to prove these, you can actually just look them up, and you should be able to find some proofs online, because these are very, very, very sort of popular proofs, and yeah, you should be able to find them online. Okay, so now we're going to talk about the pigeonhole principle. Okay, so this thing that we call a pigeonhole principle is not a proof strategy anymore. So we've developed two very, very powerful proof strategies already. Now we're going to learn to apply them to learn some more concepts. And so before we do that, we sort of, it's sort of a definition, but our problem is going to be taking place in this world where pigeons live in holes. Okay, we're going to assume that pigeons live in holes. Okay, so we put pigeons into their holes by choosing one hole for each pigeon. Okay, so like a similar analogy is if we were sort of like putting toy balls into different buckets, then that would be just like putting pigeons into their respective holes. Okay, so hopefully that makes sense, and now we're going to prove the pigeonhole principle. So the pigeonhole principle is as follows. If we have n plus 1 pigeons, okay, n plus 1 pigeons, and we have only n holes in which to place them in, and remember, we can't have half a pigeon or anything like that, okay? So we're going to assume that n is just an integer. So, and also you can't have half a hole. So n is an integer in both of these cases. So if we have n plus 1 pigeons and only n holes in which to place these n plus 1 pigeons in, we have to prove that at least 2 pigeons must be in one of the holes. In other words, one of the n holes, one of these n holes right here, will end up having at least 2 pigeons. Okay. So this is a very simple proof. Okay, and it's more of just an observation than an actual proof. So we can we can do proof by contradiction, if we wanted to be formal. So we sort of start by placing these pigeons into their holes, and we assume that we can place the pigeons into the holes such that none of the holes have at least 2 pigeons in them. Okay, so all of them have at most 1 pigeon in them. Okay, so now we're armed with a strategy. We go and we place our n pigeons into their respective holes, and we place the first pigeon in the first hole, the second pigeon in the second hole, and the third pigeon in the third hole, right? And we go so on and so forth, not placing more than 1 pigeon per hole, right? Now by the time that we reach n holes, right? So for example, if we had n equals 7, so we had 7 holes, we placed 1 pigeon in each of the holes, right? We and by the statement of this problem, we actually have 7 plus 1, which is 8 pigeons. So we have 8 pigeons and only 7 holes. Okay, so we place 1 pigeon in each of the holes, each of the 7 holes. However, we have 1 pigeon remaining. Okay, and you can see that more generally with if I have n holes, then at the end of placing 1 pigeon in every single hole, I actually am left with n plus 1, or sorry, 1 pigeon, because I started with n plus 1 pigeons. Okay, and then that 1 pigeon has to go in some hole, right? However, we have filled all of the holes with 1 pigeon already. So now, no matter where we put the remaining pigeon, it will end up in a hole that has more than 1 pigeon, or 2 pigeons, right? So basically, this is saying that no matter what strategy you take of putting the pigeons into their holes, if you have n plus 1 pigeons and only n holes in which to place them in, 2 pigeons are definitely going to end up in the same hole. At least 2 pigeons in some hole. Now remember, all of the rest of the n minus 1, sorry, the rest of the n minus 1 holes, they only have 1 pigeon. However, one of the holes has 2 pigeons, so that right away contradicts our assumption, and therefore it is unavoidable to have at least 2 pigeons in one of the pigeonholes. Okay, so if this doesn't make sense to you, sort of rewatch it, think about it for a second, and just maybe try an example with balls and buckets, or draw it out. Okay, hopefully that made sense to you. And hopefully it was easy enough for you to realize that it was more of an observation than an actual proof. And if it didn't feel obvious to you, don't worry about it. That's fine. But now we're going to generalize this proof. Okay, so we're going to generalize it so that if we have n times k plus 1 pigeons, and we want to place them into n holes, okay, and so n and k are both integers, because remember, can't have half a pigeon, right? So if we place these amount of pigeons into n holes, we have to prove that we must have at least 1 pigeon, k plus 1 pigeons in at least one of the holes. Okay, so we do this by proof by contradiction again. Okay, so we come up with some strategy. So remember how basically we're trying to disprove this, right? We're trying to say that, oh no, I don't need k plus 1 pigeons in at least one of the holes. I can manage with just putting k pigeons in all of the holes. That should be fine, right? So basically we're putting up to k pigeons per hole. And if we put k plus 1 pigeons in the hole, then we're sort of violating the conjecture, or our assumption. So we're just going to stick to k pigeons per hole at max. Okay, so now we have a strategy. We can place up to k pigeons per hole, but we can't place any more, right? And if we're able to show that with this strategy, you can sort of fill up all of the holes without placing k plus 1 pigeons in any of the holes, then we will have proved we will have disproved the conjecture, right? So now we go across the n holes and we place k pigeons in each one of the holes. And if you think about it, if you're placing k pigeons into n holes, you're essentially doing this right here. So you're placing k pigeons per hole, and you have n holes, and that gives you that you have placed a total of n times k pigeons. Okay. However, remember we started with n times k plus 1 pigeons, right? So now at the end of our so-called strategy, now we have 1 pigeon remaining. And where to put that pigeon? No matter where it ends up. Remember, right now, every single hole has k pigeons in it. So no matter where we place the last pigeon, it will end up in a hole that will now have k plus 1 pigeons in it. So we've disproved our initial assumption, and therefore we have proved the conjecture, which is that it is unavoidable to have k plus 1 pigeons in any one of the n holes. Okay, so go over that logic again, try to make sure you understand it, and sort of this is like we're sort of attempting it with a strategy, right? So make sure that makes sense to you, that we're trying to make the best case scenario. We're looking at the best case scenario and we're saying that even the best case scenario will fail. Okay? And so hopefully you've reviewed all of this. And now I am going to show you the pigeonhole principle graphically. So remember, we have these balls and buckets, right? Sort of analogy for the pigeonhole principle. So instead of pigeons, we have balls. Instead of holes, we have buckets. And we have 17 balls, okay? We have 17 balls, and we would like to place them in 4 buckets, okay? So we want to sort of like we place 4 balls in each bucket, right? We're trying to disprove the conjecture and try to see if you can sort of relate how this 4 times 4 plus 1 equals 17 is related to this n times k plus 1. Here's a hint that n is equal to 4 and k is equal to 4. So that right there, see how this statement right here, this conjecture right here relates to this example. Okay, so now remember our strategy, right? We're trying to disprove that you don't need to put 5 balls in one of the buckets. So we put 4 balls in each bucket, not going over the 5 ball limit. Then we go 4 balls again, 4 balls again, 4 balls again. Now we have this 1 ball remaining. Because we had 17 balls we started with, 4 balls, and then 4 buckets. That gives us 16 balls that we've taken care of. But there's 1 ball remaining. So we have to place this in one of the buckets, right? But no matter where we place it, let's say we place it like right here, right? Now this guy will have 1, 2, 3, 4, as well as this extra 5, and that violates the conjecture. Or sorry, that violates the initial assumption. If you're going to sort of relate it back to this conjecture right here. So I want you to find out how this example, go over the example again, and try to find out how you can make these 2 examples just the same. Okay. So the generalization is not as easy to grasp, but it's still pretty intuitive when you think about it. Okay, so this generalization has some applications of its own as well, and especially in basic like competition math problems. But it can also be used to prove more advanced theorems. Okay, but we're not going to be covering that in this video. Okay, we will maybe cover that some other time. So for now, let's just try to restate our conjecture in the form of a theorem. So if we have at least n times k plus 1 pigeons and we must place them in n different holes, we must have at least k plus 1 pigeons in one of the n holes. Okay, now we've proved that. So now just try this problem out. This is, as I was saying, it can be helpful on some competition math problems. So just try this problem out. Hopefully you'll give it a go at it. And now let's move on to prime numbers. Okay. And at the beginning of this section, I want to sort of say something that is widely used in math. So this is the if and only if statement. So when we say that statement A is true, if and only if statement B is true, we're basically just saying that statement A is true if statement B is true, and then and then we're saying that statement A can only be true if statement B is true as well. So we're essentially saying that statement A is equivalent to statement B. That's literally all we're saying. And another way to think about it is that if we say if statement A is true, then statement B is true, and if statement B is true, then statement A is true. So those are several different ways to think about this statement if and only if. So think about this for a minute. If I say that a number is even, and if I say that for statement B, so this is statement A right here, and statement B is that the number is divisible by 2. We put these together with an if and only if, right? Because these two statements are equivalent, right? So we get that the number is even if and only if the number is divisible by 2. Okay? So this means that a number is even if the number is divisible by 2, right? So that's just by definition. By definition of an even number, it's divisible by 2, right? So if a number is even if it is divisible by 2, that's true, right? A number is even only if it is divisible by 2. Well, if it's not divisible by 2, then it's going to be an odd number, right? That's not even. So a number is even only if it is divisible by 2. Okay, so try to see how these two statements right here, these two statements are in essence equivalent. Okay, and this statement right here, if and only if, is an equivalence statement. It's trying to say that two arbitrary objects or statements are equal. Okay. And it's sometimes abbreviated as IFF. So IFF stands for if and only if. And if in math you see IFF, don't think of it as a typo for if. It's usually not a typo. Okay. So now we're going to discuss about prime numbers. Okay. So prime numbers are arguably some of the most important numbers in all of math. Okay, and we'll see this because prime numbers are actually the building blocks of all numbers. So we start off with a definition of a prime number, okay? So the definition of a prime number is that a positive integer greater than or equal to 2, so first of all, positive integer has to be greater than or equal to 2, it's prime. If and only if, so remember this statement, if and only if. So a positive integer greater than or equal to 2 is prime if and only if it is divisible by 1 and n and none of 2, 3, 4, 5, 6, all the way to n minus 1. So it's divisible. So a prime number is divisible by 1 and the number and nothing in between. Okay. So note that for any positive integer n, right, that is composite, meaning, so composite numbers are actually any numbers that are not prime, or any integers that are not prime. If they're not prime, they're composite, and if they're not composite, they are prime. So a composite number, remember, by definition, if it violates this definition, it can be written as a times b, where a times b are greater than 1, but also less than n. Okay, so for example, 9 is a composite number that can be written as 3 times 3, and 3 are, or 3 is in the middle of 1 and 9, so it violates the definition for prime numbers, right? And because it violates definition for prime numbers, it is a composite number. And you might be thinking, like, why do we have this restriction right here? Well, we have this restriction because the number 1 is not prime. It is also not composite either. It's special because it's, so when you, in math, right, it's very sort of interesting because when you don't multiply any numbers together, it turns out that we define that to be 1. So when you take no numbers and you multiply them together, in math we say that you get 1. It may seem a bit strange, but that's where we get it from. So 1 is defined as being neither prime nor composite. Additionally, if you think about it, if 1 was considered a prime number, then everything else is sort of composite because prime numbers, or sorry, like some other prime numbers, they would be divisible by a composite number, or sorry, divisible by a prime number, and we'll talk more about this a little bit later. And don't worry if that didn't make sense yet. So, so now we're just gonna try to find the value in prime numbers. Why are they so important? As we will see, the fundamental theorem of arithmetic tells us that every positive integer greater than 1 can be expressed as the product p1, so where p1, p2, all the way to pm are prime numbers, p1 to the power of k1, so for some arbitrary value of k, and then p2 times k2 times p3 times k3 to the power of k3 times all the way to pm to the power of km. And as I said before, all of these p's are are prime numbers, and k1, k2, all the way to km, those are positive integers, and these are whole numbers. Okay, and so what you get from this is that basically a number can be broken down into different prime factors. Okay, and this is called prime factorization, when you break apart a number n into p1, p2, all the way to pm. This is called the prime factorization of a number. So in order to prove this conjecture, we must first prove, or we must prove two things, okay? First, we must prove that every number has a prime factorization, okay? Next, we must prove that the prime factorization of any number is unique. Okay, so there is no other prime factorization for a number. So these two parts are actually different. They're part of the same conjecture, but they are different. So we solve them both separately. Okay, and essentially, when you separate these two, you find that it's a very powerful problem-solving tool. So you write what you want to prove, and then you can prove it in multiple stages first. So that's very powerful. So first we prove the first part, of course, that every number has a prime factorization. And we use this thing called strong induction, and we will be introducing that here. So strong induction is very, very similar to normal induction. It's founded on the same basic ideas and principles, but it's a bit different, okay? So our base case is the same. So we prove a number, we prove a statement for its base case, okay? Then we assume, remember last time, like in the in induction, we assumed that the statement worked for n equals k, and we tried to prove that it works for n equals k plus 1. In this assumption right here, we are going to assume that it works for n equals a plus 1, n equals a plus 2, all the way to n equals k minus 1. Okay? And then this is our inductive hypothesis. And then we take the inductive step, which is that we say that basically we prove that because the statement is true for all of these numbers, we can use that finding to tell us that the statement also holds true for n equals k. Okay. So now let's get back to the fundamental theorem of arithmetic. Okay. We're trying to prove the fundamental theorem of arithmetic, and we're trying to prove that every number has a prime factorization. Okay, so we are going to start with 2 because 1 is neither prime nor composite, remember? So because 2 is prime, or actually here is a good time to sort of tell you that 2 is prime, because what is 2 divisible by? Well, 2 is divisible by 1, it's divisible by 2, and, well, nothing else. It's not divisible by anything else, any other positive integers. And because of this, 2 is prime, based on our definition of prime numbers. Okay, so this is our base case. And so since 2 is prime, we can just write the prime factorization as 2 to the power of 1. Okay, or just 2. Remember, our prime factorization is defined as some prime number to the power of something, right? So since 2 itself is a prime number, we can just write 2 is equal to 2 to the power of 1. In other words, 2 is equal to 2. The prime factorization of 2, or any prime number for that matter, is just itself. Okay, so and then we're done with our base case. Okay, now we do our induction hypothesis, in which we assume that the statement or our statement that the prime factorization of a number exists, so like all numbers have a prime factorization, that statement holds true for 2, 3, 4, all the way to k minus 1. Okay, and now we try to find whether or not k itself has a prime factorization. Okay, so we're assuming that all the statement that we're trying to prove holds for all of these numbers. And now we're going to use that to prove that it holds for k as well. Okay, so remember, k is either prime or composite. There is no changing that. It's either prime or it's composite, right? Other than 1, all positive integers are either prime or composite. Okay, remember that when k is prime, its prime factorization is simply just k. So we have found that the prime factorization is k. So if k is prime, then it satisfies our conjecture. Okay, so now we assume that the statement holds true for for 2, 3, 4, all the way to k minus 1, right? So now we're trying to prove that the statement is true for k, where k is composite. We already proved it for the case if it's a prime number. Now we're trying to prove it if it's a composite number. And remember, we said that if it's a composite number, k can be written as x times y, where x and y are positive integers that are greater than 1 as well as less than k. Okay, and the remark on a previous slide will show that to you. Okay, and so clearly they must be less than k, right? So we that's how sort of we defined it, right? So if it's greater than 1, it also has to be less than k. Okay, so by our inductive hypothesis, both x and y have prime factorizations, right? Because we assumed that everything from 2 onwards to k minus 1 has a prime factorization. And x and y are both a part of that set, which means that x and y also have prime factorizations, whatever they are, right? So we assume that their prime factorizations are like, for some general form, p1 to the power of j1 times p2 to the power of j2 times p3 to the power of j3, and so on, right? And we can simply just multiply these two, and then we get p1 to the power of j1, p2 to the power of j2, p3 to the power of j3, all the way to pm to the power of jm, then q1 to the power of i1, q2 to the power of i2, q3 to the power of i3, all the way to ql to the power of il. Okay, so this right here is the form of a prime factorization, right? So we found that if k is a number greater than or equal to 2, it has a prime factorization. Okay, whether or not it is prime. So if it's prime, it's just that number. So if it's prime, the prime factorization is just k. And if it is not prime, it's composite, then we can break it down into x times y. And by our inductive hypothesis, x and y both have prime factorizations. We can just multiply those prime factorizations together in order to get k in the form of a prime factorization. Okay, so now we've proved the first part of what we wanted to prove. Now we have to prove the second part. The second part is that every number k has a unique prime factorization. So we can use proof by contradiction. So we start by supposing that a number n has two prime factorizations. Okay, so we assume that the opposite of the statement is true. We assume our statement to be false. So we assume that it's not unique. Prime factorizations are not unique. So we assume that you can write it in two different ways. And let's say that our prime factorizations are like this and like this. And over here, we have just, all we have done is, let's say we had p1 to the power of p1 to the power of j. We just sort of expanded out those p1s, okay? So these are all prime factorizations, which are not necessarily, these are all prime numbers which are not necessarily different, okay? So we're going to prove a lemma first, and the lemma is that every prime number p, which divides the product of a and b, so this notation right here means that p divides a times b, okay? So every prime number p that divides a times b satisfies p divides a or p divides b. In other words, if p divides the product of a and b, it has to either divide a or it has to divide b. And remember, p is a prime number, so we're going to use that in our proof. So we suppose that in the representations of n, so actually, like, this statement over here is actually a very obvious statement over here. So we can you can sort of prove that on your own if you want, but we're gonna just use this because and the intuition behind this is that p is a prime number. So if it divides a product, then it has to divide either a or b, because in the prime factorizations of a and b, the number p has to show up. Okay, so we're interested in the representations of n, and we suppose that so remember, n can be written as in the form of 2 prime factorizations, and we suppose that one of the pi's is not any of the qj's. Okay, so this may seem a bit abstract, but all we're saying is that if so basically like all of the, if we take a certain pi, or for example p1, that this is not equal to q1, q2, q3, q4, or all the way to qj. None. So p1 is not equivalent to any of the qj's, and we must have that p1 is not sort of equivalent to any of the qj's, because uh, sorry, we must have that p1 is not equivalent to any one of the qj's, because remember we said that the prime factorizations are not equal, which means that these two forms right here, these two forms right here are not equivalent to each other. Okay, so because it's different, we have two different prime factorizations. And that means that one of the numbers over here at least has to differ from each other, right? Otherwise you end up having the same prime factorization, right? So we're going to assume that one of the pi's is not equal to any of the qj's. Okay, so now we have that, remember, pi is in the prime factorization of n. So obviously it divides n. And n can be written as q1 to the power of i1 times q2 to the power of i2 times q3 to the power of i3, all the way to ql to the power of il, right? So therefore, remember, by this lemma down here, remember, so if p is a prime number and it's dividing the product of a and b, it must either divide a or it must divide b. And so you can extend that to this right here. So p divides the product of all of these q's, and therefore it must divide one of the q's, right? And remember, both pi and all of the q's, they are primes by definition, right? They're in the prime factorization. They are primes. So if they divide each other, that is the same as saying that the two primes are the same. And you can sort of try out a few examples on your own in order to show that if a prime number divides another prime number, the two prime numbers are the same. However, we're only concerned about the exponents for now, okay? So let pm equal qn for some m and n, okay? And those are raised to the powers jm and im, okay? In. And assume that like for contradiction, remember that im is less than jm. Okay, so the power that p is raised to is greater than the power that q is raised to. Okay, now we consider when the number that you get when you divide n by qn to the power of in. So we get, remember, the prime factorizations, right? So the prime factorizations, if we write them equivalent to each other and we just divide by this number over here, we get that over here. So on this side, I'll explain this side in a second, but we get on this side, remember, we're dividing by this guy right here, and this guy used to be a part of the prime factorization. So now you have q1 to the power of i1, q2 to the power q2 to the power of i2, q3 to the power of i3, all the way to qn minus 1 to the power of in minus 1. Then you don't have any qn to the power of in because you divided by that, right? Okay. And then remember PM is equal to Qn, right? So when you divide by this right here, you essentially, for PM, you essentially get PM to the power of Jm minus In. So you're dividing PM to the power of Jm by what is in essence PM again to the power of In. Okay, remember that PM and Qn are the same, and I know I'm moving a little bit fast, so I recommend you rewatch this part very carefully in order to understand this. So because PM and Qn are the same number, when you divide PM to the power of j by Qn to the power of I, right, you get PM to the power of j minus I. And then you just add the subscripts, of course. But that's in essence what we're doing over here, okay? Hopefully you understand that, okay? And then, if you don't understand this whole dividing thing, then just understand that we're just dividing by this, and this is the result that we get, okay? Because we assumed all this stuff up here. And now on this right side, there is no Qn, right? The Qn has disappeared. On the left side, the PM, which is in essence the Qn, right, is on this side. So you have a prime factor that is on this side, but is not on this side. And therefore, they're not really equal, right? So if you have a prime number that divides this side over here, but that same prime number does not divide this side over here, then that leads to a contradiction, right? And that contradicts our initial assumption that n has two prime factorizations. And therefore, we know that every positive number greater than 1 has a unique prime factorization. I know that was very involved and convoluted, and I tried to make this as simple as possible. There may be more simple proofs out there for the fundamental theorem of arithmetic, but this was the one that we showed. So in essence, what we were doing is we were writing the prime factorization in two different ways. And then we said that we found that some of the prime factors, like at least one of these two prime factors, have to be equal to each other. And therefore, because these two prime factorizations are different, then the power that this guy is raised to must be different from the power that this guy is raised to. And we actually proved that that has to be false. And we end up proving that the prime factorization is different on both sides. And so this right here is a false equation, and it contradicts our initial assumption. So I want you to sort of take your time to read through this, read through the logic of it, and sort of determine whether or not you agree with this, okay? And hopefully this makes some sense to you, okay? And what I want you to take away from this, we just proved this, but what I want you to take away from this is that prime factorizations are a way for us to break down a number into its prime factors. And then, so is a way to break down the numbers into the prime factors. And there's only one way to do this. Okay, so remember, we use strong induction over here, right? So, like in the first part of our proof, I believe, we used strong induction So we're going to just define it formally in the form of a theorem. So in strong induction, this is a proof strategy that works similar to induction. There are three different parts to a strong induction proof. First is the base case, where you prove it for some number a. Then you assume that it holds for a plus 1, a plus 2, all the way to k minus 1. That is your assumption, inductive assumption, or inductive hypothesis. And then you say that because I know that it holds for all of these guys over here, we can also say confidently that it holds for k. And because it holds for a and a plus 1, because it holds for a, it must hold for a plus 1, then it holds, because it holds for a and a plus 1, it holds for a plus 2, and then so on. It's sort of similar to that domino principle we talked about before. Okay, so now we are going to say the fundamental theorem of arithmetic once again. The fundamental theorem of arithmetic is that every positive integer n greater than 1 can be sort of broken down into prime factors like this. So a prime number to the raised to the power of some number times another prime number raised to the power of some other number, all the way to, well, another prime number raised to the power of some number. And this right here, this form right here, is called the prime factorization of the number n. I want you to attempt these two problems and sort of see if you can use the skills of prime factorizations to try to find out the answer to these problems. Okay, so hopefully you tried that out, and these are very, very easy to confirm. You can very, very easily search it up, and you will find out the answer to these problems. They're very generic problems. So now we will go on to proving that there are an infinite number of prime numbers. Okay, so we're still in the prime number section, and we're trying to prove that there are an infinite number of prime numbers. Okay, so there's a very, very, very famous proof for this. It's a rather, like, it's one of my favorite proofs. So what you do is you say that, okay, you do proof by contradiction. So you say, okay, let's suppose that there are only a finite number of prime numbers, okay? And then we say that, okay, the prime numbers that are in a finite number are P1, P2, P3, all the way to Pn. Okay, now we multiply all of these prime numbers together, okay, and then add 1. Just consider that number, okay? So we have all of these prime numbers, and this is our finite set of prime numbers, and now we say, now we find that, now we consider the number P1, P2, P3, all the way to Pn plus 1. So now, because it's a prime number, it is, because it must be a composite number, right? Because it can't be a prime number. All of the prime numbers over here, were covered over here, right? That's what we're assuming our entire list of prime numbers is. So let's see what let's try to break it down into its prime factors. Well, in order to do that, we have to find some prime number that divides it. Okay, well, what about P1? Does P1 divide this number? Well, no, because it is equivalent to 1 mod P1. If you think about modular arithmetic a little bit, then you will find that it's equivalent to 1 mod P1. Or an easier way of thinking about it is that when you divide this number by P1, you get some quotient, but you get a remainder of 1. Okay. So Well, it's not divisible by p1. Um, well, how about p2? Let's try p2. Okay, we divide it by p2. We divide this number over here by p2. But what do we get? We get some number with a remainder of 1. Okay, and then you find that if you divide it by any of the prime numbers in this list over here, or in this list over here, you will get that the prime, or sorry, that prime number does not divide this number over here. It always yields a remainder of 1. And you can think about that for a minute, and think about why that is true, because it's, for example, for p1 times some number plus 1. And so that number right there is not divisible by p1. Okay, so hopefully that gives you some intuition. And doing this, we can find that this right here is not divisible by any prime number. But then if it's not divisible by any prime number, it doesn't have a prime factorization unless it is a prime number itself. Well, it can't be a prime number itself because we covered it right over here. Well, that means that we have an infinite number of primes. We have disproved our hypothesis that there is a finite set of prime numbers. So, therefore, there must be an infinite number of prime numbers. Infinite number of prime numbers. Okay, because of our contradiction. Okay, so go over that again and read through the text and listen to what I said carefully if you did not understand that. Okay, and now we're going to move on, because now we've proved that there are an infinite number of prime numbers. Let's move on to saying our theorem. So this is more of an we're establishing this, that there are an infinite number of prime numbers. Okay, so intuitively you can think about it. If you find the first few prime numbers, you can get this intuitive sense that there might be an infinite number of prime numbers, but this was a rather more logical way to prove that same idea. Okay, now we've learned about prime numbers, and now I want to move on to an idea which uses prime numbers. This idea is the LCM. LCM meaning lowest common multiple, and GCD. Right now we're not going to be covering the LCM, but it's part of the same class of topics. So we're going to be focusing on the GCD, which is a topic that we saw earlier as well. Okay, so we're going to be talking about the GCD of two numbers, and so the GCD of like two numbers can be found by comparing the prime factorization of the two numbers. Okay, so from the prime factorizations, you can find what is the maximum power of a prime number p that divides both a and b. For example, our example earlier was 2 and 4. What is the GCD of 2 and 4? We can find the prime factorizations first and use that to help us. So we find the prime factorization of 2. Well, since 2 is prime, that's just 2. We find the prime factorization of 4. Well, that's 2 squared. Now we try to find what is the highest power of a certain prime number that divides both of the numbers. Well, 2 is the highest prime number, that 2 to the power of 1 is the highest prime number power that divides both numbers, and therefore 2 is the GCD because no other prime numbers divide both numbers. Okay, so now that we know a little bit about theoretically how to calculate the prime factorizations of two numbers, we will try to find out if there's a better way to find the GCD of two numbers, because This is a bit of a pain, sort of finding the prime factorization, especially for large numbers. Even though the prime factorization of something like 4 is very easy to find, um, prime factorization of large numbers can be very daunting. So let's try to find an easier way to do this. Okay, so we're going to use this thing called the Euclidean algorithm. Okay, so the Euclidean algorithm is, I guess you could call it a lemma, but it's very, very, very helpful in finding the GCD of two numbers. And so this right here is the lemma to the Euclidean algorithm. And so it says that if a and b are non-zero integers and k is an integer, then the GCD of a and b is the same as the GCD of b minus k multiplied by a. Okay, so essentially what we're saying is that the GCD of a and b can be changed into the GCD of a and the GCD of, the GCD of a and b minus k times, some k times a. Okay, so it suffices to show that the GCD of a and b divides b minus k multiplied by a. Okay, so first we say that if d is the GCD, okay, d is the greatest common divisor of a and b, then a is equal to dx for some x, and b is equal to di for some y. Then we say that because d, x, and y are relatively prime, so we try to find so basically d, x, and y are relatively prime, and that follows from the fact that d is the GCD of a and b. Because d is the GCD of a and b, x and y must be relatively prime to each other, obviously, and you can think about lowest terms of a fraction, and d must also be relatively prime to those. Okay, and so we get that. D doesn't have to be relatively prime to them. Only x and y have to be relatively prime to each other. I'm sorry about that slight confusion right there. And that means that the GCD of x and y is 1. Okay, think about lowest terms of a fraction. If we take a divided by b, what's the lowest terms? X divided by y, right? So that's some good intuition for you. So we get that x and y are relatively prime to each other, and because of that, the GCD of x and y is 1. Now, b minus k times a, we substitute the values of b and a, and we get d times y, which is just b, minus k multiplied by d times x is just a, right? We get that is equal to d, we factor out the d is equal, d multiplied by y minus k multiplied by x. Okay, so therefore b minus k multiplied by a is divisible by d, and therefore the GCD of a and b is equal to the GCD of a comma b minus k multiplied by a. Okay, so now the Euclidean algorithm, we're going to use an example to try to clarify how to find or how to work with the Euclidean algorithm. So let's try to find the GCD of 144 and 270. Okay, so we're trying to find the prime factorization of these two numbers first. But then we see that these are pretty huge numbers, and they have a lot of prime factors, and that counting right there would be a little difficult, and so we turn away from that. However, in our last example, if you let A equal 144 and B equal 270, we know that the GCD of A and B is the same as the GCD of B minus K multiplied by A for some K. And then if we just take K to be equal to 1, we replace the values of A and B, we find that the GCD of 144, 270 is the same as the GCD of 144, 270 minus 144. In other words, the GCD of 144, 126. We can actually flip this around, doesn't really change anything, and we get the GCD of 126, 144. Now, as you can see, we've reduced the complexity of the problem, because we used to have these huge numbers. Now we just have these like smaller numbers, still pretty big, but they're smaller numbers. Now what can we do? Well, if something works one time, then you might want to try it again, because it can simplify your work even more, right? So this simplified our problem a little bit. If we want to simplify our problem more, why not try the same thing all over again? So what we do is we just put this at the beginning, and we just perform the GCD of A comma B is equal to GCD of B A comma B minus K times A when A is equal to 126 and B is equal to 144. So we just perform the same thing that we did with GCD of 144, 270 to the GCD of 126, 144. We did the same thing again, okay? So notice how let's have this right here, right? We're going to take A comma B minus K multiplied by A, right? We're going to just reduce the problem. So this is GCD of A comma B. We're going to reduce this to A comma B minus K multiplied by A, okay? Where K is equal to 1, and we replace the values of A and B, okay? And then we get the GCD of 126, 118. Oh, sorry, just 18. And we can flip that around to get the GCD of 18, 126. Okay, so let's try this again, because we got this number 18, which is such a small number. Let's see if 126 can be chopped down as well. Okay, so now we can subtract as many 18s from 126 as we want. So we end up subtracting 7 18s, because that's how many 18s go into 126. And we find that the GCD of 144 and 270 is 18, because the GCD of 18 and 0 is the same as the GCD of 144 and 270. And quite obviously, the GCD of 18 and 0 is 18, because 18 is the largest number that divides both of these numbers. Well, because 0 is divisible by anything, and 18, the largest number that divides 18, is 18. So make sure you understood that from this example, we were able to use the Euclidean algorithm to simplify this problem into this problem right here. And we found that the GCD is 18. And we can more broadly categorize our Euclidean algorithm, or sort of state the algorithm out into its steps. And so in the last example, we used the Euclidean algorithm to sort of simplify the complexity of our problem. But now we can generalize our example in order to compute the GCD of A and B for any numbers A and B. So if we're trying to compute the GCD of A and B, we rearrange these two numbers so that the second number B is larger than A. Okay, so B is larger than A. That's sort of obvious that the GCD of A and B A and B is the same as the GCD of B and A, okay? We're not really changing anything, so we're just sort of rearranging it. Now, we say that if A is equal to 0 or B is equal to 0, then the final answer is the non-zero number, okay? So let's, in our last example, we ended up with this number right here being 0. Then the other number, which is 18, ends up being our answer. And then we're done. However, if they're not equal to 0, then consider the number b minus k multiplied by a. And you sort of choose k, so that, choose a number k so that b minus k multiplied by a falls under the range of 0 to a. So it's in the range of 0 to a, okay, where k is an integer. And so basically we have reduced the complexity of the problem from a number b that was greater than a to a number b minus k multiplied by a, which is less than a, but still greater than 0, of course, or greater than or equal to 0. Okay, now we sort of do this thing right here where we swap the two numbers, right? And then we swap the two numbers so that a is greater, if a is greater or if b is greater, depends on which, but we always want the greater number on the right hand side because that's the number that we're going to be subtracting stuff from. Okay, and now we're going to rename these so that a is on the left and b is always on the right. Okay, so now we have a is this guy over here and b is this guy over here. Okay. Okay, so that was the Euclidean algorithm right here. So if you follow this pattern for any numbers a and b, it's very much easier to try to find the GCD of the two numbers. Okay, so let's think over this last theorem, the Euclidean algorithm, and make sure this makes sense to you, and see how it applies to the examples that we just did of the GCD of 270 and 144. Now let's take an extension of this algorithm, so a specific case or an application of this algorithm. And this is called the Bézout lemma. So the lemma is the GCD of A and B, where A and B are positive integers, is the smallest positive integer that can be expressed as ax plus by, where x and y are integers. So since A and B are both multiples of GCD, right, which we'll call D, so A and B are both multiples of D by definition, of course, every number in this form, right, ax plus by will be a multiple of D, right? Because if A is a multiple of D, B is a multiple of D, and you can try this out for a few values, then ax plus by is a multiple of D, okay? And so the smallest positive number that could be in this form is D. Therefore, we just have to, the only thing that we have to do is show that D can be written in this form, and then we'll be done, okay? And we'll use the Euclidean algorithm to try to do this. And so we can actually show that every number that we get in the Euclidean algorithm is in this form, and then use that to try to prove our lemma. Okay, so we're going to use induction. So the base case is the first and second numbers, quote unquote, produced by the Euclidean algorithm, and the first two numbers are a and b themselves, right? That's what you start with. So a and b themselves, they are, of course, they can be written in this form ax plus by if you just allow um, x to be 0 or y to be 0 and the other one to be 1. Okay? So we've proven this for our base case, which was highly trivial. Now we'll prove it for the inductive hypothesis. Or sorry, we'll make our inductive hypothesis. Okay? So we're going to say that the numbers that come from our Euclidean algorithm are Bn, B subscript n, for some integer n. So the first number that was produced is b, right? So the first number that was produced by the Euclidean algorithm was b, so that is b0. The second number is b1, which is a. The third number, which is denoted by b subscript 2, is b minus k multiplied by a, right? And then so on and so forth. So because of our base case, remember, we can assume, so our inductive hypothesis, right? We can assume that bn minus 1 and bn can be written in this form, ax plus by. So now we will be using that fact to, so first we're going to let bn minus 1 equal ax n minus 1 plus by n minus 1, right? And so this right here is of the form ax plus by. Okay, and then bn is also can be written in a similar form, ax plus by. So now we just need to prove that bn plus 1 can be written in this form as well. Well, how do you get bn plus 1? How do you get there? Well, remember, the Euclidean algorithm tells us that we have to define bn plus 1 to be bn minus 1, okay, and then minus k multiplied by bn, right? So that is the definition of our by the Euclidean algorithm. That's what we do in order to find bn plus 1. And remember, bn plus 1 is just like we're reducing the complexity of the problem, remember? So so those are the numbers that we get from the Euclidean algorithm. So by the definitions of bn minus 1 and bn, remember, by the inductive hypothesis, we assumed that it can be written in this way. Bn minus 1 can be written in this way, and bn can be written in this way. We just substitute those values in to this equation up here. And we get that bn plus 1 is equal to bn minus 1 minus k multiplied by bn. Okay? And wait, that's just this equation right here. Now we just substitute this value. We just substitute ax n minus 1 plus by n minus 1 with this value right here. Okay, and similarly, we substitute the definition of bn from the inductive hypothesis for bn. We get this right here. And we can rearrange this. We can factor out, we can multiply and factor out in order to find the form of this equation such that it's a multiplied by some number plus b multiplied by some number, and that is bn plus 1. So remember, what are we trying to prove? We're trying to prove that bn plus 1 can be written in the form ax plus by for some numbers x and y. Well, if you take x to be this number right here, and y to be this number right here, you get a times x plus b times y, right? And that is in the form ax plus by. And therefore we have shown that bn plus 1, which is written in this form, can be written in the form ax plus by. And that concludes our proof. So basically, what we've done over here is we've shown that every number from the Euclidean algorithm can be represented in this form, and therefore the GCD of the the GCD of A and B, which is also one of the numbers from the Euclidean algorithm, can be represented in this form. And so that means that D, or our GCD of A and B, can be written in the form AX plus BY. And because it's the lowest number that can possibly be written in that form, we get that D, or the GCD of A and B, is the lowest number that can be written in the form AX plus BY. Okay, and so this concludes the class today. And so what we covered was we covered both the proof by contradiction as well as proof by induction, and we also did proof by strong induction. We also did the pigeonhole principle, the generalized pigeonhole principle. Then we moved on to prime numbers, prime factorizations, as well as the GCD and the Euclidean algorithm. And then we discussed Bézout's lemma, which is what we were doing just now. Okay? Hopefully you understood some of these things, and you are this made you more interested in mathematical proofs. So mathematical proofs show a lot of insight and a lot of understanding about a certain subject. So in order to do these kind of things, you would have to know the Euclidean algorithm in and out, right? So that demonstrates true understanding of a certain concept. So I implore you to research more on proofs and try to see if you can advance your career in proofs and become more interested about it. Hopefully you enjoyed this video. Thank you for watching.